Okay, here are the solutions to the 3.3 activity on how derivatives affect the shape of a graph. So at number 1 here, we're just asked to find the critical numbers, the intervals on which the function is increasing and decreasing, and state any local maximums and minimums. So to do that, we start by taking the derivative. G prime is 3x squared minus 2x. Set that derivative equal to 0 and factor, and we get critical numbers of 0 and 2/3. Those two critical numbers define 3 intervals on the x-axis. Negative infinity to 0, 0 to 2/3, and 2/3 to 0. And then I'm using the pieces that I factored the derivative into, which are here and here, to determine whether it's positive or negative. And so on each of those intervals, I've determined whether x and 3x minus 2 is positive or negative, and then I've thought about their product, and I get that g prime is positive, then negative, then positive. So that means g is increasing from negative infinity to 0, decreasing from 0 to 2/3, and increasing from 2/3 to infinity. And that gives us a local maximum at 0, 1, and a local minimum at 2/3, comma 23/27. That's what you get when you evaluate g at 2/3. Okay, I'm going to do something similar down here in part B, which is the function is x to the 5/3 plus 5x to the 2/3. So I left this one to work through here. So I've taken the derivative just using the power rule. It's 5/3 x to the 2/3 plus 10/3 x to the negative 1/3. Now, to find the critical numbers, we need to solve 5/3 x to the 2/3 plus 10/3 x to the negative 1/3 is equal to 0. There's a couple of ways you could do this. This x to the negative 1/3 is in the denominator. You could give a common denominator of x to the negative 1/3 and see what happens there, but it might actually be a little bit neater to factor here. This factoring doesn't always jump out right away, but we can do it in this way. Both terms have a 5/3 in them. They certainly have an x in them, and then in this case, like often when we factor out the smallest thing of x that's in every term, right? So up here, we could factor an x out of both of these terms in g prime because it was the smallest power of x. So let's try to do that again and factor out the smallest power of x, which is x to the 1/3. Okay. Well, let's look at the second term. 5/3 x to the negative 1/3. Well, the x to the negative 1/3 came out. 5/3, what do we have to multiply that to get 10 is just 2. So we have x plus 2 here. Now, let's see, from the first term, we factored out a 5/3, so there's no coefficient. So we have x to some power. And I want to know, now I'm going to add exponents. So negative 1/3 plus what is 2/3 is the question I would ask. And negative 1/3 plus 1 is 2/3. So there is the factoring. So I can think of this then as 5/3, or 5 times x plus 2 over 3x to the 1/3 is equal to 0. So that gives us critical numbers of negative 2, because that's going to cause this whole thing to be equal to 0, and also 0, because that's where this first derivative is undefined. Okay? So now we need to take those critical numbers and look at the appropriate intervals here. So the smallest one is negative 2, so we need to look from negative infinity to negative 2, from negative 2 to 0, and then also from 0 to infinity. The 5/3 term is always positive, so it's not going to play a role. So I guess we can leave the 5/3 term out, but if we want to be exact, let's put it in. 5/3, we need to know what's happening to x plus 2, and we need to know what's happening to x to the 1/3. And that will allow us to say something about f prime, and then f. Okay, let's draw this in. 5/3 is always positive. X plus 2, negative 3 plus 2, if I take a test point, is going to be negative. Over here, negative 1 plus 2 is going to be positive, and then I'm adding positive things. X to the 1/3, so that's the cube root. So the cube root of anything negative is negative. Well, these first two intervals are negative things, so their cube root is going to be negative. And the cube root of anything positive is positive. So what do we get here? F prime of x, I get negative, negative, positive is going to be positive. Negative on this second interval, right? Two positives and a negative make a negative, and then positive. So f of x is increasing, decreasing, increasing. So let's see, we go from increasing to decreasing here. So that gives us a max. It's a local max at -2. Oh boy, I got to evaluate this thing at -2. And we'll just write f of -2 for now. And the other one we can handle easily is a min, decreasing to increasing, a minimum at 0, and we evaluate that function at 0 and we get 0. Okay, f of -2. -2 to the 5/3 is not going to be very simple. It's going to have some cube roots of 2 in it, so we'll leave it as f of -2 for now, especially since we're out of space. Okay, let's graph this thing by completing the following. X-intercepts, critical values of the second derivative, increase or concave up, concave down, inflection points, plot and sketch. Okay, so I've done a bunch of this here. The x-intercepts are going to occur when the function is equal to 0, so those happen at x equals 0 and x equals 3. Then the critical values are going to happen when the derivative is equal to 0. So the derivative is 3x squared minus 6x. We factor, we get 0 and 2. And we go ahead and this is the same function as above, right? Oh, no, it's not. We get 0 and 2. We create the intervals of increasing and decreasing. We get increase, decrease, increase. We get a max at 0, 0, and a min at 2, -4. Okay. And then let's see. We take the second derivative. To think about concavity, we get 6x minus 6. Set that equal to 0, factor, we get x equals 1 as a potential critical value, and we can figure that out. So let's see, we get plus 6 is always positive, x minus 1, 0 minus 1, negative, 2 minus 1, positive. So that means the second derivative is negative, positive. This means f of x is concave down, and this means f of x is concave up. So this change right here at 1 gives us an inflection point at 1 comma, let's see, when we put 1 into our original function, we get 1 minus 3, so 1 comma -2. Okay, now I asked you to sketch this thing. I didn't do a really good job here of giving you the right axis to do this on, but we can do it. So we know we have an inflection point at 1, -2. That's a change in concavity right there. Okay, let's up here. We have a maximum at 0, 0. I've already plotted that one because it was one of my x-intercepts. And then we have a minimum at 2, -4. So we have a minimum at 2, -4. Okay, and let's see. We are increasing up to 0, 0. Then we go to decreasing. Change concavity. We hit the x-intercept again at 3, so I think we have everything we need. Let's see. We are increasing, so let's see, at -5, we're probably going to be pretty small, but we're going to sketch it. So we're increasing up to this maximum. We're concave down until here we switch to concave up. We hit this maximum, and then now we are increasing. So the blue points are x-intercept. Here's our maximum at 0, 0, our minimum at 2, -4, and here's our change in concavity at 1, -2. So there's a rough sketch of this thing. Maybe not the best graph we've ever drawn, but we have, let's see, let's label these things. X-intercept, x-intercept, and local max. Here was the point we got as our local minimum. And here was the point we got as our inflection point. Okay, see if you can press on to the textbook homework for section 3.3. As you can see, graphing these things with derivatives just takes some patience. First derivative tells us about increasing and decreasing. Second derivative tells us